So, general math students, we're going to do a second three-dimensional type problem. And these typically can be quite challenging because, once again, we're representing a three-dimensional situation on a two-dimensional page. And it can be difficult to visualize what's occurring. So, of course, in class we'll do lots of these examples, and at the same time we'll try to recreate these situations in three dimensions, just in a scaled down version. But you'll see what I mean in class. So anyway, let's try this one as we would do it on paper. Now, we have a sky lantern, which is up above ground, floating in the air, but it's floating to the east and then to the north. So we have a situation where we've got, three dimensions: east, north, and also up in the air. Now, that means we need to draw this diagram obliquely. And rather than north being directly up the page, oops, I want the pen. North needs to be in this direction on the page. So that's north. And of course, the opposite to north is south. Now, east and west is a little more conventional to what we'd be used to if we were reading a map. They just go across the page as usual. So up the page, up into the air is up the page. So upwards like this would be something above ground. So let's have a go at drawing this diagram and solving this one. Like the previous three-dimensional question, we're going to need to do two calculations to get to the final answer. So we're told that the sky lantern starts at a certain point. Now, I'll say that the starting point can be, say, right here. And it's blown to the east, 205 metres. So east is in this direction. And to the north, 180 metres. So north is oblique. It's going this way. Now, the sky lantern is above the ground, and that's the premise of this question, is to find the vertical height. So here it is up here. I'll draw a dotted line for this. We want to find that height, and I'll do a little picture. You guys are going to love my artistic talents. There's a sky lantern, like a little mini hot air balloon. All right, so this might be difficult to visualize what's occurring here. To try and help, I will I'll shade in the triangle in the base plane. Maybe that will help. So, see this triangle? This is the triangle that's lying flat on the Earth. That's the Earth's surface where I've just shaded. So, we want to find the height. So the first thing we're going to do is calculate, before we do that, we are given some other information. The straight line distance to the top of the lantern, 620 metres. So that's from the start. It's probably not all that obvious the way they've written that, but we should state that straight line distance to the top of the lantern. So from here, from the start, straight up like this, is 620 metres. So if you were standing on the ground and you looked up at the lantern, the distance away would be 620 metres into the air. All right, so let's solve this one. So I'm going to call this side here x1. I'm going to find this side, this black dotted line, first. Now, it might not be immediately obvious to you that you should do that, and thinking, I wonder why we do that. With experience, with practice, you'll get really good at seeing, that's what I've got to do first. Get that answer first, and then I can get the next part. So it's just going to take some practice. Okay, so once again, I'm taking this triangle and I'm ripping it out of the 3D diagram and drawing it flat on the page in 2 dimensions, which is much more like what we're used to. Now, because we've gone directly from east to north, this forms a right angle here. That's the 205 metres, that's the 180 metres, and this is our shaded base plane triangle. So see how, from east to north, we know that that's a right angle in there. Even though it looks bigger than a right angle, that's only because it's drawn obliquely. That's actually a 90-degree angle. That can take some time to get your head around. Okay, so if we calculate x1, then we'll have this side length here and we'll be able to go ahead and find the height. So let's do that first. So we're finding the hypotenuse of this triangle, so that means a plus in between. So 205 squared plus 180 squared, which gives us 272.8. I'll just go to 1 decimal place for this one, not a big deal. How many decimal places you use, that's fine. Okay, so now, because the sky lantern's directly above this spot here, that's also a right angle. So we've got yet another right angle triangle, which I'll draw. Okay, so I'm going to draw this so the height of the sky lantern here, that black dotted line, and oops, that's not very good, give me another go at that. And then the x1, along the bottom there. And then this blue dotted line, I'll switch to blue just to show this a bit better. That's the 620. So I've taken that triangle from this 3-dimensional diagram of drawing it flat on the page here. This is our height. And this is our x1 we calculated over here, 272.8 metres. Alright, so in this triangle, you might want to pause the video at this stage and have a go at this one on your own. Then I'll do it, so I'll just give you a moment to do that. Alright, so I'll try it now. In this triangle, we're trying to find one of the shorter sides. So of course, that means that we have a minus in between. But remember, the bigger number first, the hypotenuse comes first, then minus the other side squared. Okay, so by my calculations, we're getting 556.8 to 1 decimal place. Now, if you used more decimal places along the way or went to the nearest metre, you get a slightly different answer, but it'll be pretty close, and you should know if you're right. I'm sure it's okay. But of course, if you're not sure, I'm always there for you in the classroom, so you can just check with me. So let's go ahead now and try some of those 3-dimensional Pythagoras problems. They are challenging and they can be difficult to visualise, but with practice, you'll get better at them.